let's move on to the interference of sound wave, okay, which is what we want to talk about today. Okay. All right. So sound wave, just like water wave and light wave, the important thing is that the sources of the sound, or the source of light, or the source of this one, must be two coherent waves. Okay. So for water, we put the water wave and then we put it through two slits, lah. Kan? And then for light wave, we shine the same light, but we put it into two slits. Okay, remember one slit over here and one slit over here. And the idea behind it is so that after the light or the water passes through the slit, it will diffract and make a circular shape. And then the circular shape will interfere with one another. And then okay, we have constructive lah, destructive lah, okay, and so on and so forth lah. So sound is also the same, except that we use two speakers. Okay, we use two speakers, as you can see over here. Okay, and then there's an audio generator that produces the sound lah. And usually audio generator, the sound they produce is a straight sound like just like that. Okay, it's just a steady sound. Okay, but the sound will come out through the speakers. Okay, and then if you remember the wave pattern, okay, it will still interfere with one another lah. Okay, look at my horrible drawing, but anyway, that's the idea. Okay, it will interfere with one another. Now, if you remember in the light okay, in the light, oh, sorry, hold on. Okay, if you remember light waves, when the interference happens, right, the centermost pattern is the bright pattern, right, which we call it the antinodal region. Okay, and likewise, for sound, you are going to have the K, the center one is this K, which is a loud sound. Okay, and then L is a soft sound. So you're going to have loud, soft, loud, soft, loud, soft, loud, soft. And they're going to be alternating one another. And just like light and water, the space in between the loud and the soft, is all the same distance lah. Okay, you're going to get a very uniform pattern of loud, soft, loud, soft. Okay, the reason why K is loud and L is soft because in Malay K is kuat and L is lemah lah. Okay, so bunyi kuat dan bunyi lemah. So loud sound, soft sound, loud sound, soft sound. Okay, and this is basically the setup for interference of sound wave. And if you think about it, okay, our school hall or any hall for that matter, always has the two speakers, at a certain distance lah. Nobody puts the speaker in the center of the hall. Okay, there's always the two speakers at the end there. Okay, so that the interference pattern will create a loud, soft, loud, soft, loud, soft, loud, soft. And okay, but one thing we need to remember also is that when I say loud, soft, doesn't mean that it's extra loud and it cannot hear. Extra loud cannot hear. It's not can hear, cannot hear. No. It's just loud and soft. You can still hear the sound, but it's just a little bit softer. Okay, because of the destructive interference that happens there. It doesn't mean that totally no sound together. It means if you walk there, you cannot hear anything at all. No, it doesn't mean that. It just means that the sound has become softer. Okay, and then at the loud region, the sound becomes louder. When we say louder, it's louder than the original volume. Okay, so I wish that I could turn on the audio, but I can't. So let's watch this. This is a very strange thing. Okay, so over here we have this setup lah. Okay, you have these two speakers over here. Okay, there's a card with a vertically oriented microphone. Okay, this card is over here. This is an oscilloscope to show you the wave pattern. Okay, look at this wave pattern now. How it changes. Soft, loud, soft, loud, soft, loud, soft, loud. Because extra loud lah. Okay, so as the crest and the troughs of the two waves meet, they cause interference as well as phase shifts, okay, which are related to the driving frequency. Note that in the exact middle of the track, the waves completely cancel each other because they're equal and opposite. Okay, so like in the middle, they're like really like totally no sound at all. See, there was this one moment there where there was total destructive interference. Okay, and at this moment where the sound is the loudest, is total constructive interference. Okay, so I will send you this video into the group where you can hear the sound. Okay, rather than just the sound of my voice, which is like, oh, okay, apa yang semua cakap ni saya faham. Okay, but yeah, I will send you this video later. But let's take a look at this. So the two loudspeakers are the sources of two coherent sound waves. Okay, let's talk again about the word coherent. What does the word coherent mean? Anybody? Coherent means same what? Same what? Same what? Three things must be the same.
Same frequency, wavelength, and phase difference.
Okay, same frequency, same wavelength, same phase difference. Okay, we've seen this in part 2, we've seen this in part 3. I hope that by now you understand what it means. Okay, now why is it important that they are coherent? Okay, because they are connected to the same audio generator. Okay, they are same audio generator, so they will produce coherent sound waves. Okay, now what can you observe when the two sound waves overlap? So we saw that the loud sound and the soft sound will alternate. Okay, there will be alternate loud sound and soft sound. Okay, tell me, the loud sound represents what kind of interference and the soft sound represents what kind of interference?
Constructive interference.
Okay, and Meryl, the soft sound will represent?
Destructive interference.
Okay, it will represent the destructive interference. Okay, and that's the explanation. So the loud sound is produced because of the constructive interference. Okay, and when we say loud now, again, remember, it is louder than the original sound. I'm not saying that it's and ooh, it's not just that lah. Okay, it's louder than the original sound and it's softer than the original sound. Okay, and again, the soft sound doesn't mean that the sound just totally disappear lah. Yes, there is a moment, there is a sweet spot where the sound will totally disappear lah. Okay, but if you do this in real life, definitely you cannot find that sweet spot because wherever you stand there, sure got other sounds coming in as well. Okay, so that is definitely not going to happen. But yes, there is a sweet spot lah. Okay, where the sound will be the loudest and the destructive interference will be totally destruct. Okay, there is a spot, but it's very, very hard to find because sound travels so easily. Okay, like if you stand there and you think this is a sweet spot, actually got other sound coming in. Okay, so why is this experiment done in an open area? Okay, why do we do it? Usually we do this kind of experiment in an open area because we want to avoid the reflection of sound. So if you do this in a hall, it's not a very good idea because hall, is very reflective. Okay, you do it in an open area. For example, if you do this experiment in the middle of the field, okay, the loud and the soft is more obvious. Okay, the loud and the soft is more obvious compared to if you do it in the hall, because the loud and soft, if you do it in the hall, everybody's going to reflect. Okay, the only problem with doing it in an open area like the field is that sometimes the sound will travel so far away that it's a little bit difficult to distinguish between the loud and the soft because the way the sound is just going all over the place and it's not coming back to you. Dia mungkin hilang. It can like disappear in the process of coming to you. But definitely in an open area, the interference is more obvious. Okay, you can clearly hear the loud and the soft in a much more obvious way. Okay, in a much more obvious way. Okay, let's take a look at our formula once again. Okay, and let's translate this into sound wave okay, sound wave experiment. Now we know that lambda is the wavelength. Okay, that one is normal. But can you tell me, okay, on this screen over here, where is the A, where is the X, and where is the D? How do I determine the A? How do I determine the X? And how do I determine the D? Okay, can I have who else haven't I called? Okay, can I have Ethan, Ari, and Iril to answer this? Ethan, can you explain to me what is the A, Ari, you explain to me what is the X, and Iril, tell me where is the D. Like A is the distance between what, X is the distance between what, D is the distance between what, and then I will draw it on this diagram for you.
X is between two consecutive line. Yeah.
Which consecutive line? Think about sound. Consecutive what?
So, I think that KL too. KL. There was.
Yeah. Okay, so do we want to do, that means, okay, are you telling me that X is the distance between K and L?
Yes.
Are you sure? Think about light waves and water waves. X is the distance between one antinode to another antinode. So in this K and L, which is the antinode, the K or the L?
The L.
Okay.
Okay, the K is the antinode, bahkan, because it's a
Okay.
constructive interference. So X is actually the distance between one K
To another K.
to another K. Okay, so this is the X. Okay, or instead of one K to another K, it can also be, can you give me another alternative besides one K to another K?
L to another L.
Okay, very good. L to another L. So one L to another L. Thank you, Ari. So this will be the X. Okay, because that is also interference pattern lah. Okay, which is sorry, I don't have my pen with me now. I do lah, but I'm very lazy to take it out. So the X is the distance between two constructive or two destructive. Okay, remember this. Always people will get this wrong one. Okay, they think it's from one loud to the next, loud to soft. That's the X. No, loud to loud, soft to soft, bright to bright, dark to dark. Okay, so it depends on the wave that you're using. Okay, sorry. The next person, what is the A and what is the D? I can't remember who I called for A. I think it's Ethan for A and Iril for D.
A, distance between speakers.
Okay, A is the distance between the speakers. Good. Okay, so this is the A. Okay, and Iril typed D is the distance between A and the KL. Very good. Okay, so this distance is the D. Okay, so sound experiment is pretty easy once you understand how the water and the light wave works. Okay, once you understand these two, then you know that actually interference is all about which one is constructive, which one is destructive, and that's it. Okay, and another name for constructive is antinode lah. So which one is the antinode and which one is the node? Okay, and then once you know that then this formula becomes very easy peasy lah. Okay, distance between two loudspeakers is the A. Okay, like what Ethan said. And then D is the distance between the A and the X. Okay, or the distance between the loudspeakers and where the KL is measured. And then X is the distance between the two successive loud or this is me trying to write with my trackpad. Oh my goodness. Okay, loud or soft sounds. Okay, but the key word now is this: two successive. Two successive means one loud to the next loud. Okay, not forever loud. No, okay, it's one loud to the next loud. Okay, that is the distance between this one. Okay, now let's take a look at a few applications first of interference in daily life. Okay, so one great example is this part, the bulbous bowl, okay, generates water waves which interfere destructively with the water waves around the hull. Okay, this causes calmer water waves around the ship, okay, and reduces water drag. It's very interesting. Okay, some ships have this, okay, in order to like kind of create another wave which will interfere, okay, with the water waves that are coming towards the ship. Okay, otherwise if the water waves just keep coming and there's nothing to interfere with it, right, the boat is going to rock lah. Okay, so this part here, although it looks very ugly, okay, on the ship, it looks very ugly. Actually, it's very necessary, okay, because it will, the movement of the ship will create a wave that will interfere and will cause destructive interference with the other wave lah. Second use of interference of waves is the coating on our this one. It causes anti-reflection, okay, because it will the coating okay, actually helps to interfere the waveflight. Okay, that's why you have this anti-reflection. I'm not saying that if you don't have this coating, no, let's say, I'm not saying that if you have this coating and then you put the ring light in front of you or you cannot see the reflection. Obviously, there's going to be some reflection, okay? But the idea is that the reflection will not, mengganggu kamu until you can't see, especially for the person that is wearing. Okay, the idea behind this multi-coating, okay, is to interfere with the light waves so that the vision of the person can improve. Okay, people can see better. Wow, people can see better. Sorry, there is no notes of this inside your module. Okay, but instead of writing don't need to write the whole thing lah. Okay, just want you to know what the applications are. So the number one, you just write this one lah. Bulbous bulbous bow on a ship. That's the first application. Okay, number one is bulbous bow on a ship. This is application of interference lah. Okay, so number one is bulbous bow on the ship. Number two is the anti-reflection spectacles. Okay, anti-reflection spectacles. Because if let's say my spectacles if I can see the reflection, it's going to mengacau saya tau. Okay, so sorry it's not kalau kau pandang dari sini, it's when you look into this when you look into this, you don't want to see the reflection of your own eye in your specs. It's going to be very freaky if that happens lah. Okay, that's why we have this anti-reflection coating, okay, on this part of the specs, not outside here, inside here. Okay, so that you don't see the reflection of your own eye, okay, but it'd be kind of cool, right, if you can see the reflection I think you can see if somebody is like stalking you from the back, like wow. Okay, anyway, that's the second application okay, anti-reflection coating, okay, on the specs. The third one is this one, microphone and transmitter system in headphones used on aeroplanes produces sound waves which interfere destructively with the surrounding noise, otherwise known as noise cancellation headphones or noise cancellation mics. Okay, so the noise cancellation mics, so there's this sound from the outside okay, which we call ambient sound. Okay, the dog barking, the rooster crowing, or your baby brother and sister fighting, okay. But when you wear this, okay, then you suddenly find that you can't hear them already. You can block out the noise. And what is actually happening is that the headphone itself, okay, the headphone itself is actually producing a silent sound wave that will cancel the wave that is coming, so that the only thing that you can hear is the sound of whoever you're standing at the moment okay, whoever that you're listening to. And this is a pretty good technology you kind of want to listen to your music in peace, and you don't want to have whoa, do this so so that's how noise cancellation works The headphone itself produces a wave that cancels the outside noise and makes sure that you are only hearing the thing that you want to hear, which is the music okay. And that's why noise cancelling earphones, good noise cancelling earphones, are expensive, because you think it's so easy to you think it's so cheap to produce this wave to cancel any noise that comes in, okay. And again, I'm not saying that all noise cancellation headphones are perfect. They are far from perfect, but noise cancellation has come a long way okay. I think this is a personal opinion, I think one of the best noise cancellation earphones, as in not the big, the kepala one, is there's one by Sony okay. I can't remember what's the name of the model. It's pretty good okay. You put it on you really can't hear much, okay, unless it's a very loud sound okay. Loud sounds are a little bit more difficult to cancel. For example, if there's a construction and you pass by, or if there's a loud aeroplane that passes through, noise cancellation can work somewhat, but you can still hear a little bit Okay, and again, noise cancellation. So sound waves are created by the headphone speaker. Okay, and there's a noise created by the external source. And since there is these two interfering waves, okay, they're going to cause destructive interference. Okay, again, to remind you why noise cancelling headphones are expensive, because they need to have a device inside there which has to produce a sound wave that you cannot hear, okay, but is able to cancel out the external sound. Okay, and noise cancelling technology is very hebat lah. Nowadays, they're even better. They don't just produce a general sound wave; they produce a sound wave according to what sound is coming in. Okay, but that one is like really, really, expensive and are very, very atas noise cancelling headphones lah. Okay, they can detect the sound and then they can produce a sound to counter the incoming sound. Okay, in the past, at the beginning, they just produce a general sound wave. Okay, and some of it will be cancelled, but now technology is so much better lah. Okay, that you can even sit on a plane, or you can sit on a bus or whatever, and you can't really hear the sound of the engine of the plane or the engine of the bus. Okay, so this is another one. You've reached cruising altitude on your transatlantic flight. So on flights, okay, so the crew has turned on their cool new blue time night lights and it's time to fall asleep. The super relaxing jet white noise will block out extraneous noise and calm your mind. Okay, so it's quite interesting when you sit on the plane. If you've ever sat on a plane before, there's actually this sound, okay, that somehow, okay, causes people to be a little bit more calm. Okay, but actually on the outside it's very noisy. Okay, but because of all the cancellation that has been done, okay, there is what we call this white noise, okay, from the jet. Okay, so it will cancel out whatever loud sounds there are from the outside. And when you're sitting inside the plane, yes, some people still think it's noisy. Even I think inside the plane is very noisy. But there are some which actually can fall asleep very well on a plane. Okay, because they feel that inside the plane is very quiet. Okay, especially if you're in like higher class seats, like business class or first class. So generally, you really feel that you can't even hear what's going on, like on the jet engine. Okay, and we know that jet engines are very loud. Okay, remember this guy? Okay, he's wearing the noise cancelling earphones because outside is very loud. But it kind of makes you wonder, like inside the plane, okay, why is it that you don't? Why is it that you can't really hear the car engine? Sorry, the plane engine or the jet engine very clearly. Okay, because inside the jet itself, they produce a certain sound wave to block out all this extra noise that is coming from the outside. Okay, so this is the fourth application lah. So number one is that shape of the ship there, the bulbous thing. Number two is the anti-reflection coating on your specs. Number three, and probably the most important application, is the noise cancellation earphone. Okay, the noise cancellation headphone or noise cancellation earphone. And this is the fourth one lah. Okay, is the white noise from the jet. Okay, this white noise inside the plane causes people to calm down, and they don't get so disturbed by the this one. Okay, so this is the end of our interference study. Yay! Okay, this is the end of our interference study, and so what I would like you to do is I want you to complete this tutorial 5.6, okay, which is in this one. And I'm going to give you directly the answer for what are the two questions that we have answered? Number 1 and is it number 4?
Yeah.
Okay, so number 1, since you all have already given your part, so this one I'll show you lah. So number 1, the answer is 0.67. If you use the formula, then you can get this lah. Okay, everything is in meters, so it's very easy. So among the easiest wave to use the interference formula usually is sound wave, because everything is in meter. Okay, light wave is the most mafan one. You have to change the millimeter to meter, and then it's very menyusahkan. But remember this lah, always make sure that everything is in meters. Okay. Secondly, number 4, okay, number 4, this formula, okay, this formula comes from the original wave formula that we learned. V equals to F, sorry, okay, V equals to F lambda. Velocity of the wave equals to frequency times lambda. So you count lambda by velocity, 300 meters per second, divide by frequency. Frequency is 0.5, but this one is kilohertz. So we have to times by 1000 to change it to hertz. Okay, then you get 0.6 meters. And then you use the interference formula again to get 2 meters. Okay, I want you to star this question. Okay, I want you to start this question because this is one of those questions and it's very commonly asked in paper 2 questions. Okay, they will combine both this formula. Okay, the formula that we learned in the first subtopic and the formula that we learned in this subtopic. Okay, the interference formula. Because the lambda from this first formula can be used in this lambda. Okay, for the lambda wavelength lah, kan? Can be used in the second formula. So take note of this question lah. Okay, it's a good question to remind us that actually the two formulas are connected to one another. Okay,